Frame relay, we already know for sure, we're 100% confident that indeed it is a non-broadcast multi-access technology. It is an NBMA technology. And we know that we've got address resolution to worry about, except if we're going to organize frame in those point-to-point type of connectivity options that we mentioned. We also are completely confident, as well as we know our middle name, that it is called a data link connection identifier that is a local layer 2 address. It's amazing. The data link connection identifier is only locally significant. It's a lot like gates at an airport. It's like a gate at an airport, that data link connection identifier. That is an analogy for that particular component that I absolutely love. It's like a gate at an airport. If this is a frame relay environment, and on the headquarters R router, we have Delcy 101, that's like our gate number to fly to Reno. It's only locally significant. It's just like at an airport. Reno doesn't necessarily care, right, what gate was used back at the headquarters in order to fly us to Reno. At Reno, there's going to be a gate number that's locally significant. Maybe it's 101. Notice it may match. And that's the gate number in Reno to send traffic to headquarters. Okay, so they're like gate numbers at an airport. And as such, they only have local significance. Something else about the data link connection identifier we know is that this is our layer 2 address. So this is what we need to resolve to a layer 3 IP address. There's something else in frame relay that we need to be aware of. We haven't mentioned it yet in the course, but very, very important. It's what I like to jokingly call the language of love for frame relay. This is called LMI. The local management interface. You see, the provider runs what's called a DCE frame device. That's the frame relay provider's frame relay switch that we ultimately connect with. We provide what's called a frame relay DTE device. That's the local router that we own that's on our property. The LMI is how these two devices communicate. It's their language of love to make frame relay happen. It is one of the things it's doing is it's reporting the health, what we call the status of the virtual circuit that makes up the frame relay communications. So the LMI is used for reporting on the virtual circuit health and status information. By the way, it's the local management interface that also provides the Delcy information. Sure, we learn of our locally significant data link connection identifier information through this language of love called LMI. By the way, when you go into an interface and you enable frame relay on the Cisco interface by saying encapsulation frame relay, when you do this, LMI is enabled automatically. That's how important it is. It's just a fundamental part of the frame relay. And when someone were to inspect the frame relay's PVC status with show frame relay PVC, there will be a status code that LMI shows you of either active, everything is perfectly fine, inactive, meaning we're fine, but our remote frame relay device we're trying to communicate with at, let's say, the branch office isn't fine, or deleted, meaning the internet service provider cannot help us communicate. Yikes. Frame relay. So there's a major problem involving your service provider if we see deleted status. There are three flavors of LMI. There's a Cisco proprietary flavor, which Cisco will try first, called Cisco. There's an ANSI flavor, and then there's a Q933A flavor. The good news is that Cisco routers are configured to automatically try all three of these flavors and obviously use the one that matches whatever the provider is using. We don't have to worry about this too much in the design, as the devices can go ahead and automatically detect this LMI type that is in use. Nice. We know with address resolution, we've got to solve this. We've got to design this into the frame relay implementation. If we are utilizing multi-point interfaces in our design, those are interfaces that can terminate multiple layer 2 circuits, we know that we have to provide for that layer 3 IP to layer 2 data link connection identifier resolution to IP addresses. There is two options, as we discussed. We can do it dynamically, right? We can try to have it happen automatically utilizing Inverse-ARP, or we can go ahead and configure it manually utilizing what we call frame relay mappings. And the command to do that is literally frame-relay map. When our implementers of the network are actually carrying out our design, they can verify that the name resolution is succeeding properly thanks to a great show frame relay map command that works beautifully on the devices. By the way, on a multi-point interface, you might wonder, well, what happens automatically? Well, on a multi-point interface, Inverse-ARP would happen automatically. When you go into an interface that is configured for frame relay, right when you add an IP address to that interface, right when you do that, you get the Inverse-ARP functionality enabled automatically. So what happens is requests start being sent out all of the circuits that are assigned to that interface for any supported protocol the interface is running. You can go in and you can disable this request process with the no frame relay Inverse-ARP command. But one thing that's interesting is you can never design a network that will stop responding to requests. So your frame relay speaker will always try and help somebody that is attempting to do their name resolution via the frame relay Inverse-ARP. You'll always try and help them with the resolution. We cannot disable the reply behavior for Inverse-ARP. And, I can't think of really why we would want to anyways, right? We want to be helpful as we can on the wide area network with our frame relay implementation, and we want to try and help Inverse-ARP succeed in the cloud. By the way, the Inverse-ARP behavior in our designs, it is going to automatically assist with broadcasts through that replicated unicast feature that we spoke of. So when you are doing Inverse-ARP, broadcast support is there through that replicated unicast approach. So we do those replicated unicasts with Inverse-ARP in order to give the impression of the broadcast support. So Inverse-ARP, we would find it in use in a design by default that uses multi-point interfaces. Now look at this. This is interesting, right? We have connected the R3 router to the frame relay cloud using a physical interface. And we have connected R5 to the frame relay cloud using a physical interface. So we have connected these devices to the frame relay cloud using physical interfaces. What does this mean? Yeah, sure enough, it means that these interfaces are multi-point. Yep, a physical frame relay interface, we said it earlier, by definition is a multi-point structure. So even though we are connecting R3 and R5, it looks like a point-to-point circuit, doesn't it? Because we're using the physical frame relay interfaces, this is a multi-point infrastructure. And by default, these devices are going to handle the layer 2 to layer 3 name resolution dynamically utilizing Inverse-ARP. What if you wanted to go in and design it so that Inverse-ARP wouldn't be used in this environment? Well, you can go ahead and turn off the dynamic mapping behavior on each device. We can turn off frame relay Inverse-ARP, and then we can go in with one of these frame relay mappings. Notice you specify the protocol of IP, you specify the remote IP address, you specify the local data link connection identifier, and then if you want the replicated unicast behavior, you use the broadcast keyword. The broadcast keyword is going to give us that replicated unicast behavior for the support of a broadcast type functionality. So we've got to go in and we've got to configure these static mappings if we want to override or turn off the dynamic Inverse-ARP behavior. Notice it's very interesting that these static mappings, as you would hope, do indeed override dynamic mappings. So you, as the administrator, have ultimate control, therefore, over this important name resolution process, which is going to occur in our frame relay NBMA environments. So, if you wanted to, you could take that topology that we looked at earlier, where we are using the physical multi-point interfaces in order to give R3 and R5 connectivity over the frame relay network. We could go in and we could turn off the Inverse-ARP behavior if we wanted to on both of these devices, and then we could go in and provide the static mappings. By the way, a huge error that can result on Cisco equipment is that once the interfaces come up, the physical interfaces come up, and Inverse-ARP does its thing, you can find that there are dynamic mappings to 0, 0, 0, 0. Ugh. These dynamic mappings to 0.0.0, they happen because of a clash of two features. Inverse-ARP, firing up by default and running on the particular device, Inverse-ARP clashes with something called the Cisco auto install feature. And that is why these mappings to the all zeros IP address, which we know isn't valid, that's why these mappings occur. You may have to reload your device after clearing the Inverse-ARP cache in order to get rid of these mappings to all zeros. They will indeed cause a failure in communications in your frame relay environment. So we got to definitely warn our implementers about this problem that can happen with Inverse-ARP and the address resolution. We remember that point-to-point configurations, yes, they're wonderful when it comes to name resolution, because by their very nature, we don't need to worry about this layer 3 to layer 2 name resolution. Now, one thing with frame relay that you do have to worry about, however, is because the devices are using sub-interfaces, when we configure point-to-point frame relay, we use point-to-point sub-interfaces. The problem that we have to handle is sub-interfaces won't get their DELC assignment from LMI any longer. LMI can't provide the sub-interface with its DELC information. So you have to go in and you have to manually assign the DELC to the subinterface. Yeah. Going to be your responsibility to go in and tell that subinterface what its data link connection identifier is. We got to go in there and we got to train it. That's done with the frame relay interface DELC command under the subinterface. So we could go ahead and take that R3 and that R5 device and we could create point-to-point subinterfaces. You must specify the point-to-point interface type when you are creating the subinterface. And now we just need to provide IP addresses. We need to tell those subinterfaces what their DELC are, and then everything works beautifully. Everything works beautifully. There's no name resolution to worry about because of the nature of the point-to-point connectivity. Okay, there's only one device out there that we're going to be sending our data to, and that's the device that's on the other remote end of the frame relay connectivity. So there is no concern about our name resolution. By the way, if you were to create subinterfaces and make them multipoint when you configure them, now you're right back to deciding, okay, are you going to do Inverse-ARP or are you going to do static mappings? Because now you have multi-point subinterfaces. And it's hilarious because on R1, you could literally rely on the dynamic, but on R5, for example, you might rely on the static. And this would work just fine. You see, the interface type setting and what you're going to do for name resolution, that's really only locally significant. So we can have all kinds of differences in our designs, like the main interface connecting to the main interface, or a main interface connecting to a multi-point subinterface, or a main interface connecting to a point-to-point subinterface, or a multi-point subinterface connecting to a point-to-point subinterface. It really doesn't matter. The interface type and the protocol resolution is really only locally significant. And if we properly configure the frame relay, given the local choice that we make in that design, we can have connectivity over the wide area networking environment just fine. Partial mesh configurations, partial mesh designs, should we choose to go this route, they're going to give us the most challenge, aren't they? Layer 2 circuits won't be provisioned between each and every one of the circuits. And as it turns out, really the hub and spoke is just a special type of partial mesh configuration. If we have a hub and spoke, we need to realize that the spokes, because they're not directly connected with each other, they can't resolve each other through Inverse-ARP. So if we are in one of these very popular hub and spoke topologies with our frame relay cloud, we know that we're going to have name resolution issues. And that's because of the lack of direct connectivity that the spokes have. We have to provide either additional static mappings, or we need to drop in a point-to-point subinterface approach, or we need to design the hub and spoke infrastructure so that layer 3 routing designs can solve the name resolution gaps that we have. For example, in OSPF, as we'll see later on in the course, in OSPF, there is a network type called point to multipoint. And the point to multipoint type for OSPF can be used to solve the issue of a lack of name resolution in the partial mesh infrastructure. So we can have layer 3 routing help out with name resolution issues in our partial mesh NBMA clouds. Now, the last thing I want to talk to you about for frame relay is I want to discuss how frame relay does have markings that can impact quality of service. Frame relay does have markings that can impact our QoS. For example, there is in the frame relay header a DE bit. What does the DE bit do? Well, its name says it all. The DE stands for discard eligible. Aha! So with frame relay environments for QoS, you can literally have the packet marked with the DE bit set, and you're now telling the frame relay provider, look, we understand that you may be experiencing congestion at some point. When you're experiencing congestion, don't freak out if you have to throw this packet away. So you mark your unimportant traffic that you're sending through the frame cloud, you mark it with the DE bit set so the provider knows to avoid further congestion, it can go ahead and throw away that unimportant packet. Something else that can be configured in a frame relay environment is called forward explicit congestion notifications and backward explicit congestion notifications. This is really cool. The frame relay equipment, if configured to do so, can notify devices of congestion and can result in a nice slowing down of the sending rates. So if we have these frame relay nodes, right? We have these frame relay nodes that are speaking this beckon and fecken. This device can send forward a forward explicit congestion notification. And this forward explicit congestion notification can say, look, there is congestion, we need to slow down. Now, what's the deal with the backward explicit congestion notification? Well, the fecken marking is moved forward, but what if there is no return traffic to send backwards? We want to make sure everybody knows about congestion in all of the paths, forward and backward. So what if there is no return traffic to send? Well, we enable beckons. And what a beckon is it's a test frame that is created. It's just a frame of nothingness. There's no significance to it other than to carry the beckon bit setting backwards. So now this test frame flows backwards, and it's a way to notify the return path that there is congestion. So feckons are marked in traffic moving forward, and then these beckon test frames can be created and sent backwards to ensure devices in the return path understand that there is congestion in the network. How do the devices respond to these feckons or beckons that are received? They slow down. The idea here is to have the equipment slow down the rate at which it is sending traffic so that we don't have further congestion. Well, you've become well-versed in the issues surrounding wide area networking, and this section specifically for frame relay. So this exam review question for you would seem remarkably simple, I bet. What are two options for name resolution in a frame relay environment? Sure. Two options for name resolution are going to be to create those static mappings or to engage in the Inverse-ARP dynamic configuration. Two options. And these options we know, let's review this further, these options we know are going to exist in our multi-point configurations. In a point-to-point configuration, there is no name resolution to worry about. No name resolution to worry about if we're in a point-to-point type of configuration. Excellent. Well, in the next lesson of our CCDA bootcamp, we're going to wrap up our tour of these various WAN technology protocols by talking about a whole bunch. We've got SONET yet to talk about. We've got MPLS yet to talk about. We've got DSL. We've got cable. So we'll go ahead and in our next lesson, wrap up our tour of these wide area network technologies by taking a close look at some other great WAN options.